Hey guys, welcome back to CADclass, where this week we are continuing on with our reprinted series where we 3D print an entire 3D printer piece by piece. Last episode we went over how to CAD model and 3D print the bolts, and now we can finally use them to assemble our 3D printer's frame. Quick recap of the rules: we are trying to replace as many parts as possible on the Ender 3 with 3D printed replacements. I can only make minor modifications to the parts in CAD, and the final project needs to be as close to the original Ender 3 as possible. Some of these parts are going to be larger than the print volume of our printer, so obviously we're going to be having to print them in half and then reassemble them later. But per the rules, I'm not allowed to use any glue or screws because the Ender 3 doesn't, and that would be cheating. This video is going to cover all of the challenges and hurdles that we went over when we modeled, printed, and assembled our plastic printer, and then at the very end we're going to be printing a little benchy so we can see just how bad an all-plastic 3D printer really is. To start off with, we have 6 pieces to print out: the top frame, the 2 verticals, the outer base, and the middle base. Each part needs to be minutely modified to allow for our larger bolts in the previous video, as well as any other components in the future episodes. There's tons of engineering, CAD, and design considerations that goes into this project, and we are really excited to see just how far we can push this idea until something fails. And to me, that's just the fun of engineering, to have a ridiculous idea and see just how far we can possibly push it and maybe see if it works. So with all that out of the way, let's get started on the top frame. The first major change that we need to do is to simplify the aluminum extrusion profile as much as possible. These parts, as you can imagine, are made by extruding aluminum. That's how you can get this really complicated shape without needing to do any milling or any CNCing whatsoever to produce a really complicated but incredibly strong part, even though it's made out of very soft aluminum. All of those grooves and T-tracks in the aluminum part that gives it so much strength is actually going to be a real challenge for us for printing. So one of the first things that we can do is actually smooth over all the walls to make it as easy as possible to print. I started off by jumping into Fusion and then projecting the outer profile. Then we can join some of the outer walls and extrude it so it's all one continuous mass, but with consideration that we keep the T-tracks exactly where we need them. For example, the wheels on the X, Y, and Z axis run along the grooves on the vertical pieces, but the grooves on the front and the back of the surface serve absolutely no cause for us, so we can just get rid of them. If we were to keep these grooves, then it would mean a much more difficult print because it would need so much support material just to get grooves that we're not going to use. Next, we need to increase the size of the holes to make way for the larger bolts that we made in the previous video. And in this case, we actually need to add on a very special type of hole called a counterbore. Most of the time when you think about holes, you're talking about a simple hole. This is a hole that either passes all the way through your material, known as a through hole, or only passes partially way into it, called a blind hole. Most of these holes are made with drill bits going into softer material like wood, plastic, or aluminum, and they give you pretty round holes. Just to go on a tangent really quickly, technically, the holes that you get from a drill bit that has 2 flutes or grooves that spiral all the way down the shank do not give you a circular hole. It actually gives you a slightly rounded triangular hole because the flute has 2 points that bounce in a triangular shape. Back to the holes though, if you have a bolt that looks like this, a socket head bolt, then you actually need to have a secondary stepped hole to account for the head of the bolts. In a very similar concept, if you have a countersunk bolt, then you need a countersunk hole. These are the type of bolts where they have a flat top and angled underneath, and to make sure that the top of that bolt is totally flush with the surface, you then need to carve out the very top edge of the hole so it has a nice chamfer that the screw or bolt can go into. Going back to the counterbore bolt, you can actually buy specialty drill bits that just have a smooth shank for the threaded section and a larger diameter drill for the head. Having the surface of the frame be flush with the very top of our bolts is going to be really important for the base of our frame, but for the very top section, because we don't have that much material, we actually don't care if the top of these bolts are just a little proud. Now that this part is all done in CAD, we can export it and open it up in Prusa Slicer, so we can cut it up into 2 pieces that we can then assemble later on. Last time we used Cura as our slicer, but this time we're going to be trying out Prusa Slicer, because they have a really fantastic feature where you can take a model and cut it, but with a dovetail joint in the middle, so that you can assemble your parts and fit together really exceptionally. Both slices have lots of really fantastic features, and you shouldn't discount one just because another is really fantastic, because they both are incredibly powerful. To use the dovetail feature in Prusa Slicer is incredibly easy. Make sure you have your model selected, and then click on the cut feature on the left-hand side, and it will automatically add in a cut to the dead center of your part. You can change the cut from planar to dovetail, and then you can adjust all of the sizes of the width and the depth of the part. The concept of a 3D printed dovetail is exactly the same as in woodworking, where if you make the pins or the tails too thin, it's very likely to be the place where that bit of material breaks off and then the joint becomes ruined. The rule of thirds works really well here. If you split up the linear joint into 3 sections so both parts are equally strong. As an experiment, I set the tolerance of the width and the depth to 0.0 millimeters, and it actually caused me just a little bit of trouble later down in the assembly. After printing and removing the part from the build plate, I pressed the 2 parts together with my arbor press, and without any glue, the parts held really fantastically. Now the joint actually worked completely fine, but because there was no tolerance between both of the walls and there was quite a lot of pressure built up, I ended up with quite a substantial bow between both the parts. But luckily, because this is just the top section and none of the rails actually slide along it, this minor bow actually doesn't affect the build whatsoever. As I printed more and more of the pieces for the frame, I slowly increased the tolerance by 0.1 millimeters until I found that 0.4 millimeters was about in the sweet spot, where it was tight enough that you didn't actually need any glue for the 2 parts to be held together, but it did require the pressure from an arbor press to fully seat the 2 parts together. Next up are the 2 vertical posts, and just like the top section, the whole idea of the CAD is simplify, simplify, simplify. As we said before, the only places that need the grooves are the outer smaller sections. The front and the back can be completely smoothed over. To make the part just that little bit stronger, I did push out the walls of the bottom of the groove just a little bit so I have more material and then more beef, but unfortunately, what I found during the assembly is that this now didn't allow the T-nuts to pass through, so even though I thought I was going to make it better, I ended up completely screwing myself over. The other modification is that I needed to make some changes to the existing holes on the left and right posts. On the right, I had to modify the holes to allow for the PSU, and on the right, I needed to modify the 2 threaded holes at the bottom for the Z motor. Now for safety concerns, I actually don't want to replace the housing of the PSU or the power supply unit to a plastic frame because fire, but I will have to keep the steel bolts that pass through the frame and then into those threaded holes on the housing. And a similar response has to be taken to the Z motor. It has pre-fitted holes onto it so that it mounts correctly, and so I need to use the steel bolts even though I don't want to. Now, one of the problems that I have with printing these vertical posts in 2 parts and then attaching them together is that I need to make sure that the grooves that the wheels run across are as straight as I can possibly make them. And that means, because we learned from the bowing on the other part, that I need to make this a sideways dovetail joint. This added feature means that I do need to add some support material to hold up the pin and the tails on both sides of the joint, and that's going to require a new tool that I haven't actually played around with yet: paint on supports. The idea with most slicers is that you decide that you want support material and then you can go back and define where you don't. And for the most part, this works, but it can be a little annoying. The alternative on some of these slicers is that you add support material, but only in a block form, which is fairly tricky and not super adaptable. The idea with paint on supports is that you have a much finer brush, so you can put support material exactly only where you need it. If you use the paint on supports tool on the left-hand side and you draw a small section on your model and try and slice it, you'll find that it doesn't add any support material to it. The trick is that you need to change the supports in the top right from none to for support enhancers only. Then you can reslice your model and the supports are now added only to the area where you painted. Up next is the middle base piece, and this actually gave me a little bit of trouble because there's two cutouts on this aluminum part. One dead on the center for the Y-axis to fit into, and then one off to the left-hand side for the Y-loom to fit through. As far as the CAD went, it was very similar to the other parts. Simplify the outer surface, expand the M3 bolts so we can use them for a future episode, and expand the width of the Y-axis track to account for the 3D printing tolerance. And this was all fine and dandy until it started printing. Without me noticing, one of the back corners started to lift and peel, which essentially ruined all of the layers in that back corner. Thankfully, this defect is purely aesthetic and not functional, so I don't need to reprint this entire part from scratch. That being said, let's go over why it failed and what I could have done to fix it. Very simply put, it got cold. When you're 3D printing, the plastic wants to cool down nice and slowly, and if it goes from being a molten plastic to frozen or solid too quickly, it'll actually peel away from the print bed and cause a ripple effect that changes all of the next layers. The reason for this is that the Ender 3 only has one heating element for the bed. That means it may be the perfect temperature in the very center, but as you get closer and closer to the corners of our build plate, it gets successively colder. Most of the time this isn't too much of an issue, but when you have large prints with sharp corners, that's when they love to curl. One of the fixes for this problem on the CAD side is to add a little fillet to the edge, so instead of a perfectly sharp corner that can lift up really easily, there's now a nice smooth radius. The other way is to extend the perimeter on that first layer, and traditionally you could use a brim in your slicer for this. But if you have a large model that only has a couple sharp corners, that may not be super necessary. In fact, you can actually add a very special brim only to the corners called mouse ears. Mouse ears are little sacrificial circles of plastic that you can place in the corners of print, and because it's only one layer, as soon as your print is done, you can just peel it off and have minimal post-processing. One of the nice things about Prusa Slicer is that you can actually do this natively inside the program. Right-click anywhere in the workspace and click Add Part, Gallery, Helper Disks, and click OK. Then you can move this circle to the corners of your print and get it printed. And for a first-time use, this worked fantastically. The little circles held down the parts on the next print and were really easy to remove, so I highly recommend that you guys add this to your 3D printing arsenal. Finally, let's work on the outer base pieces. For some reason, I never noticed this, but the outer base pieces are actually perfect mirror images of each other. This makes life really easy because any changes that I need to do for both the pieces, I really only need to make to one of the parts, and then I can duplicate it and mirror that part across a vertical axis in my slicer so I can get both parts for doing half the work. These got a similar treatment to the rest of the parts where we smoothed the outside and then made the holes larger to accept our 3D printed bolts, but that's where things just got a little funky. Because the original Ender 3 use M5 bolts, they actually pass through each other in this component and miss each other by just a few millimeters. My much larger bolts don't have that luxury. As you can see in the assembly, there is a healthy amount of material that is in the way and blocking the bolts from actually being passed through. I decided to press on with the CAD knowing that it might be a problem later, but I may have a little bit of wiggle room with the bolts, but as it turned out, this was actually a huge headache to fix. But this minor problem actually turned out to be a really nice ethos for the entire project in a whole. I know that I'll be running into problems in the future, and I'm just gonna have to figure out ways around it to get the final project to exactly where I want. After this print was done, the accumulation of all the tips and tricks that I learned just on this one project alone made the final part look absolutely fantastic. And remember, this is not printed on some spectacular expensive machine. All of these parts are printed on the original Ender 3, completely stock, no special treatments. I even made all of the slicing completely bog standard. Going back to the CAD, I did need to print off these two extra orange pieces that essentially acted like collars so I could use the normal N5 steel bolt to pass through our 3D printed middle base to then get secured into the metal Y-axis. But don't worry, we are going to be turning that into a fully plastic Y-axis in a future episode. Now that all of our pieces are 3D printed, we can finally start the assembly. First off, all the pieces that we cut dovetail joints into need to be joined together and being pressed into one piece using my favorite tool, the arbor press. I grabbed my T-handle Allen key and started to screw the M10 bolts through the outer base pieces into the middle base piece, making sure not to over tighten them. Just like the aluminum threads on the real Ender 3, if you over tighten those bolts and strip the threads, it's game over. Then I screwed the shorter M10 bolts through the top frame and into the vertical frame pieces, making sure they're on the correct side and in the correct orientation. Now you can see the problem with the final print. The through holes to secure the base onto the frame are completely blocked. To make some room for the bolts, I grabbed my rotary tool and tested out a couple different ball end cutters, sanding discs, and milling bits, but in the end, all it took was some time and patience to make sure all of them fit perfectly. Here's a look at one of the bolts we had to carve material away, and here's what it looks like beforehand. We took out a lot of material, but in the end, we still have the majority of the thread left over, and the head of the bolt is completely intact. So this bolt, even though it looks very chewed up, it is still completely functional. Now we can screw the base into the verticals, and I found that the best way is to actually put the frame on its side and then screw the bolts in through the base. I only say this because that's how I would assemble a normal Ender 3 in real life. You tip it on its side and then screw it in from the bottom. And it was the first time in this entire build that I actually felt like I was really making a 3D printer from scratch. Now that the frame is all assembled, I can move some of the components over from the original Ender 3 onto our reprinted printer. So let's start off with the PSU. I unscrewed the two bolts of the M4 variety and moved it over and reattached it onto the right vertical aluminum extrusion. Next up was the Y-axis, which was a lot more difficult just because it had such a huge loom of cables going into the motherboard, and the sheer weight of the Y-axis really put it into perspective how light the entire frame was. It was made with less than 1 kilogram of material, and so the entire printer now can just be picked up like that. It's ridiculously light. Currently, we don't have the motherboard housing or the screen holder or anything like that printed or modeled, so that's going to be done for a later video. So for now, they're just going to be dangling in place. Now that the vast majority of the printer has been moved over, we can now unscrew the bolts on the very top of the frame and then slide on our X-axis. The spool holder on top was a little bit of a challenge, not because it was difficult to assemble, just because I was kind of cringing that it was likely to break. We've got a full kilogram of material on top, and it's really only being held up by some T-nuts that are clamped onto a plastic frame, and I was fully convinced it was going to break, but it didn't. It completely survived. And finally, the last problem to tackle was the Z-axis limit switch. As we said before, I made the T-slot just a little bit smaller to increase the strength of the part, and unfortunately, that means that this part no longer slides into place. And so I did the only thing that I could think of in the moment. I zip tied it in place. I'm not very proud of it, but it did work. Now this printer is all ready, we can start to home our axis and get started to print our very first 3D Benchy on the mostly plastic 3D printer. This is officially the first 3D Benchy that we've got in this entire series, and as we add more and more pieces onto our new printer, we're going to be trying and testing out more and more Benchies to see just how bad they get along this series. But for a first one, this looks perfectly fine. I was expecting so much of a worse result, but in the end, it actually looked pretty good. It's not amazing, but it's much better than I thought it was going to be. The entire frame is made out of plastic, and with a kilogram up top, as it was printing, the entire frame was waving back and forth, and even with that, it's still printed fairly well. I will note that the settings for this Benchy are not tremendously special. They are bog standard settings. I'm not doing anything to the slicer to make this Benchy look artificially better using special code. This is purely just the integrity and the strength of the 3D printer. The only defects that I'm noting right off the bat is a little bit of ghosting and ringing, basically because the frame isn't as rigid, which is completely expected. And some of the layers have a little bit of chatter, but other than that, if I saw this and someone told me this came out of a bog standard Ender 3, I would say, yeah, looks pretty normal. All in all, I'm really excited that this is the first major milestone in this project, and we can see just how far we can push this printer until it fails. Thank you so much, guys, for checking out this video in our reprinted series. If you want to learn more about 3D printing and CAD modeling, then you can head over to CADclass.org, where we have courses and videos over every single topic you can imagine. Thanks so much, guys, and we will see you next time.